Hi guys, welcome back. I wanted to chat with you for a little bit today about Newton's first law. And so we introed this the last time we were together, and we chatted about how Newton's first law is his law of inertia. And essentially, it looks at objects that are moving at a uniform rate. So their acceleration is equal to 0 meters per second. And the thing to really emphasize here is that when we talk about Newton's first law, this can refer to objects that are stationary, but it can also refer to objects that are moving at a uniform rate, or at cruise control is how I typically refer to these objects. So Newton's first law, we chatted about briefly during class time, but Newton's first law basically states that objects in motion stay in motion, and objects at rest stay at rest unless acted upon by an external force, right? So unless something external applies a force to the object, the motion of the object is not going to change. So if the object is at rest, if we have a cup of water on the table, that cup of water will stay at rest unless someone comes and moves that cup of water. If we have an object sliding down an ice surface and there's no friction or anything like that, that object will continue to move, much like actually an air track. If you've ever played air hockey, the puck on the air hockey table will continue to move unless it hits the edge of the table and comes to a stop, right, or changes its direction. And so that's typically what we're referring to when we talk about Newton's first law. And specifically, we're talking about an object whose forces are balanced. And what that means, if the forces are balanced, it means that the net force acting on the object is equal to 0 newtons. So essentially, whether moving or rest will be going uniform motion, so their acceleration will be 0 meters per second. And if the object is moving at uniform motion, the sum of the forces acting on the object, or the net forces, is equal to 0. Okay, so those are two really, really important concepts to make sure you've got straight in your mind, is that the object can be at rest or it can be moving, but either way the acceleration is equal to 0 meters per second squared. And if we add up all of the forces acting on that object, the net force will equal 0, because all of those forces are equal in magnitude, opposite in direction, so they essentially cancel each other out. Now I've got an example for you. This example is hanging from the roof, right, and it's attached to the roof with these metal rods, or potentially some sort of a cable or something like that. We know that the sign is fixed to the roof and it's not moving, right? It's stationary in that spot. So we know that the acceleration of the object is 0 meters per second. And it's not going to change unless someone comes here and cuts the ties that are attaching the object to the ceiling. So the object is fixed to the ceiling, it's not moving, and its acceleration is 0 meters per second squared, which means that the object is obeying uniform motion. And if we look at our free body diagram for this object, what we will note is that if we sum all of the forces acting on this object, the net force on the object will equal 0 newtons. And this is 0 newtons, not on, because that's something that people mistake. It refers to 0 newtons. And so what I've got down for you is a free body diagram for this object. And we briefly chatted about, we know that the object is going to have a force due to gravity that's pulling it toward the Earth. Now, it's not moving toward the Earth because this object is fixed to the ceiling, right? And on those cables or on the rods that are attaching it to the ceiling, there's going to be a tensile force on those cables that results from the weight of this exit sign pulling down on the cables, right? And we know that because there's two of these objects, the sum of these two forces must add up to the sum of the gravitational force, but it has to be opposite direction, right? So if we look at the net force is the resultant force, and that's equal to the sum of all the forces that are acting on this object. So in this case, we have our tension force on that first cable, the tension force on the second cable, and the force of gravity. So we sum all of these forces together, and we know that because the object is experiencing a 0 meter per second squared acceleration, we know that the sum of all of these forces has to equal 0 newtons. Okay. Another example, and so in this case, before I jump to the example, we would know that this object must be obeying Newton's first law. Another example on the outside, if our skydiver has hit terminal velocity, right, we know that at that point the skydiver is falling at a constant velocity toward the Earth, and it can't accelerate anymore because that air resistance is impeding that acceleration. And so if the skydiver is moving at terminal velocity, that means that their acceleration is 0 meters per second squared, which means that the skydiver is in uniform motion. And so if we draw our free body diagram for this particular skydiver, we know that they're in free fall, they're falling toward the Earth, they've got a force of gravity that's pulling them down toward the Earth. But we also know that there has to be some opposing force that's causing them to have reached this maximum velocity that they can't surpass. And what that force is the force of friction. In this case, our air resistance, right? Which is impeding always, friction is always working against the direction of motion. So friction is acting up on the skydiver. And again, you know that if the forces are equal in magnitude, so my arrows are equal in magnitude and opposite in direction, we know that they'll cancel out. Our net force, and this is kind of the underlying theme for this whole unit, is that the net force is equal to the sum of all of the forces that are acting on this particular skydiver. So in this case, our net force is equal to our force of friction plus our force of gravity. And the sum of these forces is going to be equal to 0 newtons. And so that's kind of the premise of dynamics, really, but Newton's first law specifically. So I've got an example for you here, and this example is something like that. Exit sign. We've got an open sign hanging from the door of a storefront. If the sign has a mass of 5 kilograms, determine the tension force on the strings. So now we're going to insert some numbers into our net force equations, and we're going to start working with calculations. So I know that the weight, like the weight that this object has, is 5 kilograms. And what I want to figure out specifically is, I know that there are 2 strings here holding the sign. What is that tension on these strings? And it might seem kind of like a useless activity, but a lot of times, not so much with an open sign, but if you think of something like an elevator or something like that, force of tension is actually really quite important, because you want to make sure that if you're going to load that elevator up with people, you want to make sure that that cable is going to be able to handle the tension that it's going to be placed under so that it doesn't snap, right? So there are some, very real life applications as to why you want to calculate a tension force. In this case, we know we have our open sign. We know that the sign is going to have gravity pulling down on it, and then the strings are going to obviously become, they're going to undergo a tensile force because the sign is weighing the strings down. So in our diagram, what I did for the exit sign, we're dealing with vectors. And so much like in the kinematics unit, whenever we deal with vectors, we have to include direction with these vectors. So I've placed my Rosetta over here, and typically we say up is positive, which is what I'm doing here. So I'm saying my up is positive, my down is going to be negative. I know that this open sign is stationary, so I know that the acceleration is 0 meters per second, and I know that that indicates that the net force on this open sign must be equal to 0. Okay, so those are two things that I know right now because the question tells me that the open sign hangs from the door, right? It's hanging there. It's not falling from the door or anything. And so I know that net force is always equal to the sum of the forces acting on the particular object. In this case, the forces acting on the open sign are the force of tension on the one cable, the force of tension on the second cable, and then gravity. So I rewrite this statement as force net is equal to force tension 1 plus force tension 2 plus force gravity. I also know that because the sign is equally hung from both of the cables, that the force of tension on each of these cables is going to be equal. The weight is going to be equally distributed amongst these two cables. So the force of tension, I can rewrite it as 2 times force of tension because I know this force of tension and this force of tension are going to be the same. Now, something that I want to introduce to you guys is this concept. Gravitational force, it's made up of the mass of the object and the acceleration due to gravity. So this Fg is equal to mass times gravity. So because they haven't told me what force gravity is, I need to, in essence, calculate what is the force of gravity. And the formula for my force of gravity is the mass of the object times the gravitational acceleration that's pulling it toward the Earth. So I've basically just from this free body diagram, I've set up my equation for this particular object. And this is the way every one of these force problems will always work out. We'll always start with our F is equal to sum of the forces. F net is equal to, and we'll insert all of the forces acting on the object. And then from there, we can expand on if we're dealing with force gravity and maybe mass times gravity, gravitational acceleration. If our forces tension are equal, we can put them together and say 2 force tension. This next thing is I know that this force net has to equal 0. So I know that if I sum all of these forces together, my overall answer would be 0. So I'm going to insert 0 newtons right here. I'm saying force tension is equal to 0 newtons, and that's equal to 2 times the force of tension. Sorry, force net is equal to 0 newtons, and that's equal to 2 times force tension plus, they told me that the mass of my sign was 5 kilograms, a pretty heavy sign, times gravity, and I know gravity always acts down, and in this case, because I said up was positive, it means my gravity is negative 9.81 meters per second squared. And if I solve for Ft, I rearrange and I solve for Ft, I get that Ft is positive 25 newtons, or 25 newtons in the up direction. I have to insert a sign or a direction on there because it is a vector. So therefore, the weight of the sign is equally distributed between both strings. So the force of tension in each string equals 25 newtons. So that's the first example. We did an example similar to this, during class time when we were talking about free body diagrams. Second example here would be a problem. A 1,500 kilogram elevator is moving up to the 5th floor at a constant velocity. So this term here is important because this tells me that the acceleration is 0 meters per second. Right, so I know I'm undergoing uniform motion, and if I'm undergoing uniform motion, I know it's a first law problem. So, and if I know if it's a first law problem, I know that force net has to equal 0. And they're telling me that the velocity is 1.2 meters per second up. And say if the elevator cable is designed to withstand a force of 20,000 newtons, how much extra kilograms can the elevator safely carry? So again, we draw our body diagram. This is super important because this is how we're going to set up our equation for solving the problem. So I know that for the elevator, there's going to be a force of gravity pulling the elevator down, and there's going to be a force of tension that's created on the cable that hangs the elevator. And I'm going to say up is positive. And with all of these problems, I always start with my basic statement. Force net is equal to the sum of the forces. And in this case, my force net is equal to my force tension plus my force gravity. Okay, so that's what I have here. And I know that force gravity, they haven't given me an actual force gravity in newtons, but they did tell me the weight of, well, they told me the weight of the elevator. So I'm probably going to have to use mass times gravity. Okay, so I've inserted that there. Now, what do I know? I know that force net has to equal 0 newtons because we're moving at a constant velocity, so we're moving at uniform motion. I know that the maximum tension that the cable can hold is 20,000 newtons. If we go over that 20,000 newtons, we have the potential of snapping the cable, and that's not good. And what I want to know is what is the overall mass that this elevator can hold in order to have this 20,000 Newton tension force. And I know gravity is minus 9.1 meters per second squared, minus because gravity always points down, and I'm saying down is negative. So if I isolate for mass and I solve, I get that the mass of the elevator that's going to give me this 20,000 Newton tension is 2,038.736 kilograms. That's what mass the elevator would have in order for the tension on the cable to be this. And so if I know that the elevator itself has a mass of 1,500 kilograms, and this is the maximum mass that the elevator can potentially have, that means that we could add a maximum amount of people to equal 539 kilograms. If our people enter the elevator, or our boxes and loading whatever materials into the elevator equals 539 kilograms, we're going to have that cable at a tensile force of 20,000 newtons. And we don't want to go over this 539 kilograms because there's potential we'll snap the cable. Okay, so those are two examples of Newton's first law problems. And like usually, guys, if you've got questions or something doesn't really make sense, I didn't do a good job explaining it, by all means, please bring it to class. We'll chat about it. We'll do some examples together when we see each other. And until then, I hope you guys are doing well. Stay safe, and we'll chat soon.